Hey, Al. I'm assuming you can hear me because I've had good luck in the last couple days, but if one of you could unmute and verify that you can hear me, I'd appreciate it.
Yeah, we can hear you.
Uh-oh. Could one of you try it again?
Hello?
Yeah, I'm not hearing that, so I'm gonna cancel this. Okay. Could you try yet again one more time, please?
Hello.
That worked. And Hosea, it was funny. I was talking to you just a few minutes ago and on the exact same setup as far as I could tell, and it worked fine then. Oh well. Let's think. Class today, I think maybe starting off with a couple administrative things, and maybe I'm going to share a screen to do that. That's a good place to start. And let's just go ahead and share that whole desktop like normal. And let's go with that. Okay, so yeah, Stat 312 today. You might have noticed if you tried to show up between 11:25 and 11:50 that I wasn't there, so that was a bummer. But then hopefully you remember to check Canvas and came back 3 to 3:50, and I talked to a couple of you then, so that was a good thing. But you know what? We can always work with it, you know? And so hopefully you had your questions answered. If you did pop by, but there are a couple of you that did, it appears, try to show up and didn't make it back at the later time slot. So maybe it'll be a chance today to talk about that. We will find out as we go. Want to mention though that if I click my way into the syllabus for class, I see something that is awesome and or concerning, and that is exam one. I've got it sort of written and up there for y'all. It's going to go live as of 5 p.m. tomorrow. There is no expectation that you're going to try it right away. As long as you turn it in by Thursday night at 11:59 p.m., that's the right way to go. And there's always someone who's going to say, but hold on, I've got DRC accommodations, blah, blah, blah. So yeah, you do what you need to do to get it done by the time that it's due. Should work out fine. I've set things up so that way if you start it in time that with accommodations, etc., you're going to finish by 11:59. It should be no problem. But I always encourage students to plan for at least an extra hour, not for the test, but if something does go wrong, you don't want to sort of feel like under the gun. Don't start the test at exactly 11 p.m. is what I'm suggesting. Okay. So there's that. And we're gonna move on into newish material in chapter 3 tomorrow. But if you have questions related to the sample exam problems, we'll have some time to talk about those. Clicking my way into where it says or exams, you can see the sample exam problems for the first exam and some very brief answers because some students always want to say, did I get it right? You try the sample exam like a practice, and if you numerically get the same number, you feel good. And if you want a more full explanation, there are fuller, more complete answers there. But yeah, there's no class time particularly devoted to spending on the sample exam questions. But you'll see from the video that corresponds to what we'll do tomorrow, there's a fair amount of student questions related to the sample exam. And so don't hesitate to ask them in class tomorrow. Not a big deal. Versus moving forward in chapter 3, I would rather you feel comfortable and confident with the course material than move on promptly. Okay. So that's what I wanted to say about the exam coming up. Second thing I wanted to note is if you click your way into today, blah, 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 there's a lab today that is related to partially the uniform and probability, Poisson probability distributions. You already have seen both of those, but we're going to be emphasizing topics like, darn it, I wanted to do one more thing. Oh, well, I didn't. In the lab, the key thing I wanted to be sure to put in the lab, I'm just realizing now I didn't put in the lab, but next time will be better. But certainly in the lab, it's emphasizing bridging the gap between those two probability distributions in probability distribution land, and then what data from those probability distributions actually looks like. And so it's going to give you a little bit more practice with JMP, but also matching up data to the corresponding distributions themselves. So with all that in mind, that's the other thing I want to mention. And then in the context of that lab, yeah, you guys have new lab groups. We saw that last week. Some of you said thumbs up on my group, and some of you said, yeah, on my group. Try to do my best. And I'm sure many of you will say, that's exactly what I wanted, by way of, a change up or perhaps sticking with your same group. And others of you are going to say, that's not exactly what I wanted, but hopefully you're happier, or I should say better yet, at least as happy as the first go round. If you find that the lab groups aren't working out for you for whatever reason, shoot me an email probably tomorrow while you're working away on that second lab. If things are going not so well in the first two parts of this week, we can fix it up. Okay, so make sure that you let me know any feedback as need be. So I think that's it for my set of administrative announcements. You might have, however, administrative related questions, so now's a great time to ask those before I move forward into something new. And I'm watching chat and not seeing anyone having typed a message there. And y'all have the opportunity to unmute and ask a question that way, but I'm not seeing or hearing. The odd thing is, like, I'm right now looking at a giant, massive blur. I was at the doctor, and you know how they do the sort of dilation of your eyes. That was multiple hours ago, and it's still not up to normal. So I'm looking around, seeing a bunch of blurry people. Okay, so John asks, on the homework, are we expected to do manually calculating or using the JMP probability calculator? Great question, John. Yeah, I don't care. I would suggest using both is a great way to go because literally you could do the do it by hand approach and then use the probability calculator to verify, or the other way around, use the probability calculator and then make sure that you could do it by hand. Because if there is a question on the exam which says be sure to do this by hand, then it'd be great to have had practiced that. There is nothing, however, preventing you on the exam from using the JMP probability distribution calculator for exam one. And I'm not saying I'm encouraging or discouraging. I am just saying, John, and the rest of you, that use the method that is quickest, that gets you the answer the most readily. But be prepared for a question that isn't going to be answered in a flexible either way. I might say use the probability distribution calculator. I might say that. Or I could even say, please do a quick screenshot and upload the portion of your JMP probability distribution calculator that verifies the following claim. Um, I don't tend to ask questions that way, but sometimes I will direct you towards using a particular method. So, John, does that answer your question thoroughly enough? Okay, but you might very well reasonably say, "Oh, but you didn't really answer it because, you just said no both." Know what's best for you. Most likely, the method that you've been most comfortable with will solve your problem. Okay. It's only in the situation where I say specifically, do it by hand, or I construct a question where you can't really do it so easily with this probability distribution calculator. That's the more challenging. And that's the nature of the frickin' question on the lab today that I forgot to include in the lab. But I'll try it in the context of, hold on. My OS is trying to update, and that would be bad for class. I'll try it in the context of the class's lab. I will sort of show you how you could use JMP to tackle a non-standard question. And that might be helpful for the exam as well. Okay, any other questions? Okay, switching gears then. How about questions from any content last Wednesday, Thursday, or questions related to homework problems that are due tonight by 11:59 p.m.? Okay. So what I want to do is move forward into talking about newish content, blending that newish content with our understanding of data. And this is sort of like the lab and sort of also like the thing I wanted to be able to show you and I forgot to put on the lab, but hey, we'll do it in class and that's good enough. What I'd love to start with is a definition of the expected value of a function of a random variable. Okay. So, there's, I guess, two different cases. One is the discrete, one is the continuous case. So we'll go with discrete in black. Or better yet, I'll just start here. The expected value of a function g of the random variable x. Okay. I'm going to say we've got these two different definitions. One is discrete. And to find that value, I would literally say summing across all of the possible x's, sum of g of x times p of x. Okay. But in the continuous case, okay, the expected value of g of x, the expected value here of g of x is equal to integrating from negative infinity to infinity g of x times f of x dx. Okay. And so you're thinking, well, first off, what the heck is that? Well, we don't use this all that often, but we use it in our understanding of the variance of a random variable. We said last time that the variance of the random variable x is, it's got another definition here, but I'm going to use the following: the expected value of x squared minus the expected value of x itself squared. Okay. And so we need to know how to find the expected value of x squared. So that just says I need to add up x squared across all of the different possible chances. So I'm going to take a screenshot of that and then sort of move forward into the binomial context. And so if x, darn it. Okay, so if x is distributed binomial, and I'm going to go with NP, and I'm going to go with, in this case, N is, say, 25, and P is, say, 0.4. So you're thinking flipping a biased coin that comes up heads 40% of the time. Flip that coin 25 times and count up the number of heads. Okay. What is the expected value of x squared? All I would need to do is to sum across all the possible x's. So I guess summing over the range I goes 0 up to 25. I guess I could get 25 heads, even if the chance of a heads is only 40%. Well, I have to put in x squared, so that'd be x goes 0 to 25. So x squared times p of x, which is just x factorial over n factorial x. And I'm just screwing this up left and right here. Let's erase this. And I'm gonna blame my eyeballs on this one, but that's not true. So let's get it right. Okay, so this is x factorial. And then, darn, I sort of screwed that one up again. This is n factorial, and then x factorial n minus x factorial times p to the power x times 1 minus p to the probability, or to the power n minus x. So you're thinking, okay, math, I could do it. Yeah, I know you could. Do you want to do that? Not really. And so the lab is going to ask us to tackle the problem of what if we were to simulate from this distribution? This is sort of like the last lab out there. So let's walk you through how to simulate a binomial with n25 and p zero point 0.4. And we'll see how we could sort of solve the problem and approximate the expected value of x squared. So I gotta get GMP up and running. And one of the things, if I've got GMP going, darn it, I've got GMP going here. This is not so helpful here, but under the upper top, if I want to file new, actually, let's go with this where it says new data table. This is like the lab last time, new data table. And notice here that I've got just this number here, this column one. There's nothing in it. But I'm going to right click on column info and I'm going to say, well, let's just give it a name. And I'm going to call it binomial, say 25.4. That's a goofy name, perhaps, but bin 25.0.4 is literally n 25 and the chance 0 0.4. So that tells me, yeah, indeed, that's the distribution I'm going to create. So it's a good reminder. It's a good variable name. And I like to say, well, what if I'm going to produce, let's go with 100 rows of data. You could put in 1,000, you could put in 10,000 if you want to do lots of simulated values. Probably the larger the value here you have as the number of rows, the more simulated data you have, and the closer the results are going to be to the truth. I'm going to click at this point in time, column properties and formula. And under column properties formula, edit formula, I have put nothing in there. And under edit formula, maybe over here, I'm going to create, and this is sort of like the lab from last time, random. Well, not uniform, normal, integer. In the lab today, you're going to use uniform, but I said binomial, so click binomial. And n, well, 25. And p is, I wish I could see here, 0.4, 0.4. So I'm going blind here. I'm assuming that this says 25.4, not 0.04. And I click OK. And so my variable, after clicking OK, this just tells me the distribution of a collection of, well, 100 of you people, you and your 99 best friends, all take a biased coin, a coin that comes up heads exactly 40% of the time, and you all flip it 100 times. And some of you get fewer heads, some of you get more heads. One of you got 8. Okay. So let's look at a histogram of this distribution. Yeah. The distribution itself, sorry, analyze the distribution will give me the histogram. Click OK and drag it over here. And let's make sure it is stacked up because it looks better to me. So the lowest number of heads that anyone got across you and your 100 best friends was about 5. And the highest was nowhere close to the 25 maximum possible here. But we had the minimum being minimum 5 and the maximum being 17 in our data set. Okay. So this is the distribution, and shoot, there's the average is 10.39. So the claim is that this 10.39 is close to the expected value. Not exactly. I mean, seriously, the expected value. If you're going to flip a fair coin, say 100 times, you get 50 heads and 50 tails. What if it's a biased coin, comes up heads 40% of the time? You would expect the outcome of about 40 heads in 100 flips of coin. What if it was only 25 flips of a coin? What's 40% of 25? It's 10. The expected value is in reality 10. What if we want to know the expected value of x squared? I don't know why I'm whispering. What if I want to know the expected number of heads? squared. Yeah, literally, you and your 99 best friends are all playing a game, and it's a silly game, but you all flip a biased coin. A coin would come up heads 40% of the time. You flip that coin 25 times, and you count up the number of heads, and then you square it. And that's your score in the game. This friend here got 10 heads, so 100 was, in fact, the value of x squared. Or your friend over here got only 7 heads and clocked 49 as their score. Clearly, a higher score is going to happen when your n is, 15. So that'd be like 15 heads, 15 squared 225. Let's just create a new column. This new column could be just called x squared. So I'm going to call x shift 6 and then 2. That literally is x squared. As a column property, I'm going to go with the formula, edit that formula, and again, it's in the wrong place. The formula I want is literally the outcome squared. So maybe what I should do is cancel that and edit the formula here. And now I'm going to look at this carefully and say, shoot, x to the power of y. Okay, so my number of heads could be squared. We could also just take the outcome x times x. This is another way of getting the same thing. And so my 10 gets me 100 as x squared. 14 squared is 196. 9 squared is 81. What's the expected value of x squared if x is a binomial with 25 trials and 0.4 as the chance of success? The claim is the typical or average value of this x squared variable should be pretty close. So let's go ahead and try analyze the distribution of your friend x squared. Click OK over here. And again, stack to be fun. And the average value of x squared is 114.55. That's the average in our data set. Our data set, which was simulated from the probability distribution. So 114.55 is pretty close to the expected value of x squared if x was binomial. And so we could approximate an answer with the software. And so that's my encouragement is if you ever get bogged down in the mathematics and you need to know what is the typical value of x squared, simulate. You could get a numeric ballpark answer that you could then later use for benchmarking your on the actual piece of paper calculations. Any questions about doing that?
Sorry, what would be like the title I could put on this type of a calculation?
Uh, I would probably give it a title approximation of the expected value of x squared. And so what I'm just going to do is sort of switch down and sort of switch over and write that up. Okay, so yeah, literally, we want to know the actual value of x squared. Okay, so what is x squared? The expected value of x squared? I don't know. But if x is binomial with 25 and 0.4 as the chance of success, we could literally find the expected value of x squared as summing across x, lowercase x goes 0 up to 25, x squared times x factorial over n factorial x, I'm sorry, n minus x factorial. Let's go backwards. There we go. N minus x factorial. I screwed it up again. I'm sorry. I screwed this up twice in two tries here. So that's not really ideal. X factorial and n factorial. And then okay, so starting over and being happy with the results because I'll get it right this time, I promise. We have n factorial over x factorial n minus x factorial. Okay, so literally this calculation We're approximating it by simulation. So the approach that we're suggesting is, I don't actually know the real value. Okay. But I guess we could simulate 100 in the lab. It's going to ask you to do 1,000 of them. Simulate 100 X's from that distribution and then create. Okay. So we're going to calculate X squared. Okay. And then find the average of the X squareds. And that should be pretty close to the expected value of X squared. So that is an approximation, a simulation-based approximation.
Why is there no p to the x times 1 minus p to the n minus x portion
Ah,
there?
because I got flustered and didn't write it down. So let's add that in. Yeah. I'm glad you asked because then it's now corrected. Okay, so yeah, literally, do I want to do this by hand? Probably not. Could I do it by hand? Yeah. Would it be a pain in the ass? Yeah. So we could find the expected value of X squared in that way. But I told you that story to tell you this one because, yeah, literally, we defined the variance of a random variable as the expected value of X squared, which we know how to calculate. And in some cases, like the Poisson, it's pretty straightforward, even though a pain in the ass, minus, and then let's go minus the expected value of X. And we could calculate that usually more equally and square it. So the book walks you through how to get that. Okay. So not too bad. Let's go show you another use of then our expected value of a function. So we're going to put that on hold and talk about what about the expected value of a plus b times x. So some constant a and another constant b. We're just going to take x, the random variable, multiply by b, and then add a. You think, let's convert the temperature in centigrade x into a new value of the temperature in Fahrenheit. I guess we're going to multiply by 5/9 and then add 32. Okay. So yeah, A and B are just constants. It's resetting our ruler. Essentially, you might move the ruler to the right or to the left, and you can stretch it out or compress it. We're just using different units. Our random variable X here might have a distribution of possible values. And if we sort of let's go with 1/2 of X. So X over 2, that's like a constant. It's going to be narrower, right? Okay, and then if we then add something, it's just going to be shifting it to the right a little bit. So x over 2 plus then a constant x over 2 plus a constant k. So it's just a matter of taking your histogram and spreading it wider or narrower to accommodate for different measurement units. My claim is that the expected value of a plus b times x is equal to a plus the expected value. Well, actually, let's even jump right further. A plus b times the expected value of x. And so I'm going to do this in the discrete case. So let's switch gears here and just go ahead and verify that that's the case. So you want to know the expected value of a plus b times x. And what we know is that's well, and again, this is the discrete, not continuous example. This is summing across all the possible x's. A plus b times lowercase x times p of x. Okay. But what we know here is this is well, we could distribute, And this is summing across all x's, a times p of x, plus then, well, b times the sum of x times p of x. Okay. And if I remember correctly, and I don't usually forget these things too quickly, actually, let's even pop the a out front. I'll just write it here and cross it off there. This here is just the sum of p of x across all possible x's. That's just equal to 1. And the sum of x times p of x, that's the expected value of x. So what we have here is a plus b times the expected value of the random variable x. If I want to know the expected temperature in Fahrenheit, I could say, let's take the expected temperature in centigrade, multiply by 5/9, and then add 32. Not really surprised. Any questions about that? Okay, so let's talk about the expected value of a Bernoulli random variable using our approach here. So for Bernoulli, so x is distributed Bernoulli with chance. So P is just the chance of success, and that means P of lowercase x is just for it's P or 1 minus P for x being 1, and for x being 0, it's 1 minus P is the chance, and 0 otherwise, or pretty much anywhere else. There's only two possible outcomes, a 1 and a 0. And so the claim is that the variance of x. Okay, so the variance of x is equal to the expected value of x squared minus the expected value of x squared. So I guess I need to find the expected value of x. And we did this previously. We found that the expected value of x is just p. So we're sort of halfway done. I need to find the expected value of x squared, and we've already done that part. So let's get into the other part, which I will go with purple. The expected value of x squared is just summing over the both possible values, x squared times then the chance of x occurring. And so I guess that's sum x being 0 up to 1. And 0, well, we don't have to worry about that one hardly, do we? Just 0 squared is still 0. And so this is just, it's going to be 1 squared times p of x being 1. That's 1 squared times p. That's just p. So overall, what we have is p is the expected value of x squared minus the expected value of x squared minus p squared. Or I could write that as p times 1 minus p. That's the more convenient way of phrasing it from a statistical point of view. So we found the variance of x. And what about then the standard deviation of x? So the sigma, if you will, that's the root of the variance. Okay, so sigma, the standard deviation, SD for standard deviation, is just the root of the variance of x, and that's the root of p times 1 minus p. And I think we're just done. We can't really simplify or make it more convenient than that. Yay! So we could find a variance pretty easily. Sort of want to move forward unless there are questions. I want to talk about the percentiles of a distribution of numbers in the percentile of a distribution, probability distribution.
Just to make sure I'm following, why are we summing from 0 to 1?
Because those are the two values for lowercase x.
Gotcha.
We're some,
So 0 and 1 are just all possible values of x because it's
yeah,
Bernoulli.
exactly. It's Bernoulli, which means it's either a 0 or a 1. It's one or the other. Okay, we sort of hinted at when we talked about the last time, John, when we at the end of class you asked about percentiles, okay, a median or something like that. We sort of did talk about median as like you line up the numbers lowest to highest and find the one right there in the middle. What about the quartiles? I think it was last class session or maybe two ago that you asked about the box plot. We're moving towards that. Okay. And so how do I find the quartiles of a distribution, or in general, the pth percentile of a distribution of numbers, number values? Okay. So yeah, literally what we're going to do is align up the numbers lowest to highest. And an approximate way of thinking that through is take the so it would be the pth percentile is the the observation and the p over n times hold on, how do I want to phrase this? Okay, so the observation p over nth of the way through the ordered list. So yeah, if I want to find the median, yeah, literally the median is, well, 50th percentile. Okay, so 0.5 is going to correspond to p. Okay, it's the p times 100th percentile is probably a better way of phrasing it. That 100 times pth percentile. So the 50th percentile corresponds to a p of 0.5. Go halfway through the ordered list. That would suggest the 25th percentile is going to be 1/4 of the way through the list. We'll call that guy Q1, the first quartile. And you're going to think 1/4 of the way through the list. A slightly better way to think about it might be halfway through the first half of your list. Anything less than the median, call that the first half of your list. Find the individual that's 1/2 of the way through that list. Or the third quartile would correspond to a person who's 1/2 of the way through the second half of that ordered list. They're at the 75th percentile. If I have a data set like I do right here, and let's clear that so you can see. This is, again, my list of numbers, and that corresponds to, no, that is not the one we were working with earlier. There we go. Here is my list of numbers, the binomial. An approximation of the 25th percentile of that binomial distribution, we could find it by saying, well, we have 100 data points from that. Let's put them in order and find out who's at the 25th percentile slot. Again, analyze the distribution of what? Of those binomials. And what we have here is our distribution. Again, I'm going to stack it up so we can see it. You can spot that the first quartile, okay, the 25th percentile, the first quartile is at 9. In our data set, 9 occurs here, and maybe I'll try and highlight this from 9 and down. That is 25%. The third quartile here is at 12, so that's 25%. The median here is at 10, and so that says 25 and 25. It's hard to really sketch it out on a histogram. I guess if I blew it up and make it look bigger, it's going to be a little bit cleaner. Okay. But yeah, you could divide the data, the 100 data values, into the lowest 25, the second lowest 25, the third lowest 25, and then the highest 25. And that will give you where you have the quartiles and the medians, the median and the two quartiles breaking. So the minimum, the median, the two quartiles and the maximum, those are sometimes called the 5-number summary of your data set. Again, minimum, first quartile, median, third quartile, and then maximum. They, with 5 numbers, summarize all of the values. We're just chopping the data up into the lowest fourth, second lowest, third lowest, and fourth lowest, or the highest fourth of those data values. Okay. And in this case, it's for a binomial. How do we actually find for the actual binomial distribution where the 25th percentile is? And so what we need to do is define for a distribution where that 25th percentile is. Let's go ahead and provide you that definition. And there we go. So the definition itself for the 100 times pth percentile of a distribution. So the 120, so let's just say the 25th percentile of a random variable x, okay? It's going to be the smallest x, smallest lowercase x, such that the CDF, or if you will, the chance that the random variable x is less than or equal to lowercase x, or if well, the probability that the random variable x is less than or equal to lowercase x is at least p. Okay, so that's a little bit tight. Tight as in precise in a mathematical sense, but what the heck? Let's dive in and make some sense out of that. As I'm going through the distribution of a random variable, there's a chance that we would have an x of 1 or 0 or less. Okay, so there's various lowercase x values. Okay, so lowercase x, and if you will, the probability that the random variable x is less or equal to that lowercase x, 0 has a certain chance. 1 is a certain chance that we are there or less. 2 is a certain chance that we're there or less, etc. And we're going to go up until we have that greater than 0.25. When we add up enough of them that it's equal to 0.25 or more, then we've found our distribution. Okay, our distribution's first quartile. So let's show you, well, we'd think approximately in the data set, it's going to be about 9 or so. You know, from the data, we have the 100 realizations from that binomial distribution. We're going to guess about 9. Let's try JMP's probability distribution calculator, because we know that that can tackle a lot of problems that we otherwise wouldn't easily be able to pull off. So let's show you how to do that and maybe clear that off. And okay, let's go back to binomial. And being 25 flips of a coin with a chance of heads of 0.4. So here's my distribution. Binomial, 25 trials, 0.4 is the chance of success. And by I, you're sort of saying, where do we have? About a fourth of the total area is to the left. You're sort of thinking maybe a fourth is like 8 or 9, somewhere in that range. If I input a probability, a lower tail probability of 0.25, what we know is, aha, when you get up to an x of 8, okay, we literally have the chance of 8 or fewer heads occurring with our biased coin. That's going to be 27.35% of the time. We've achieved the goal. The first percentile of the actual underlying binomial probability distribution, we could get it exactly. It's 8. What if we wanted the third quartile, 0.75? You'd say that's 12. Our simulation earlier told us in our sample it was 12. And we could try this for any possible probability, 0.95 even. The 95th percentile is going to be at 14. In other words, 95% of the people who try to flip this biased coin 25 times, should be getting, well, 96.56% of them getting a 14 or fewer heads. Okay, so it seems as though we're sort of scratching our way through probability. There's only one last thing I wanted to mention today, and that is our friend, the normal quantile plot. So I'm going to sort of show you a data set and ask yourself, is this a data set taken from a normal population? Yes or no? Let's see if I can pull off which data do I want to use. So I'm going to tell you, I'm going to give you an example that you're going to say, well, we know that that's not normal. It'll be easy to look at. Our distribution here is of the number of the length of these catfish. And let's just go with the flathead catfish to subset to deal with just the FCF flathead catfish. I'm going to mouse down there, right click, and select matching cells. Go over to the left here. So I've highlighted all the flathead, but the others are not selected. I'm going to right click in there. Darn it, right click over here and invert my selection, and then hide and exclude. So I'm left with just the flathead catfish remaining for my analysis. I'm going to analyze the distribution of the lengths of those flathead catfish. And you're sort of thinking, normal population or not normal? It's sort of hard to see, isn't it? Well, let's stack it up because that makes it easier to look at. So that looks like it's maybe symmetrical. Maybe because there's only 156 observations. Maybe that's like bimodal or trimodal. It's hard to know exactly. Is this perfectly following a normal curve? There is a way that we could assess this formally, but I'm going to suggest the graphic approach of the normal quantile plot. You literally just turn on this thing called a normal quantile plot, and it corresponds to a graph where, in this case, along the x-axis, we have where the data points are, in fact, and on the y-axis, we have where they should be if they're spread out evenly in probability space. In other words, across 156 observations, one of them, the smallest one, should be really small at about the 6th or 0.6th percentile. So its percentile would not be even the first percentile, the 0.6th percentile. And if we go up and down, up through the whole entire data set, the data point that's at the 0.6th percentile should be right around here on the vertical scale. And so on the vertical scale, we have where should these data points appear if they were perfectly spread out according to the normal curve. Here we have where they are from the lowest over here off to the left to the highest up here on the right. This normal quantile plot matches up our data to where they should be if the population we're sampling from were perfectly normal. I'm going to bigify that and say, you're looking for straight line. And are the bulk of the data following sort of a straight line trend? Yeah, but then it does seem as though it's sort of bent in two locations. It's sort of like going straight and then it bends and then yet again straight. It says right around here or so, we have a lack of normality compared to before. If I fit a normal curve off to the very left little bits, up to here, it says we should have more data values in this next little bunch. If you fit a normal curve off to the left, we should have more and more data than we actually have. There's fewer data points, so we're at a shallower slope. And then all of a sudden, we have a curve yet again. So like over here on the right and over here off to the left, it would suggest a lot more data should be in the middle than we have. A shallower slope, steeper, shallower, steeper. There's a lack of normality here, a non-straight line, if you will, a curved relationship. Our software will draw in for us these sort of bow tie shaped little regions. You can see this little curve. That curve is a zone of good enough. If the bulk of the data are in that sort of curve, you're saying good enough. In our case here, we'd say no, the data values fall outside that curve. That's a decided lack of normality. So I would say this histogram is not normal. It looks like it's not normal at all. So that's a good place to set you up for the homework problems assigned today. And yay, we're happy because we're making progress. Tomorrow we're going to move on into new material that is not covered on the exam. But tomorrow, if you come to class with questions about material related to the sample problems, we'll spend time talking about those so you are ready for the test. Again, I'm going to stop the recording, but hang out for a little bit. If you have any questions, I'm happy to answer those before I bail out. We'll see you soon, though. Bye-bye.